Hello, students. Let's talk about scientific research in Chapter 2. This chapter is all about how we do research. It's about science in general, so if you're in other science classes, this might be some repeated information, but we'll focus on also how psychologists do these studies. So research methods and science is all about methods. Science is a method. It's how you study things. So it doesn't matter what you study. The subject is not the thing that makes it science. It's how you study it that makes it science. So we've got a little picture of a hero down here. So superhero flying around. I study heroism, not people with superpowers. That would be pretty neat, but people who take heroic action, take extreme risks to help other people. And yeah, that is one way I've done interviews for studies of heroes. I have been doing a long running kind of test if we can make people more heroic. That's quantitative, so with numbers like statistics and math. This example over here, this is acupuncture. So you can test acupuncture. You could study it, and that would be science. This over here is an example of reaction time. So it's an early study of reaction time. A researcher would drop a ruler, and the participant is the bottom hand. They would try to catch the ruler. And the objective measure is how far did the ruler fall? What inches or centimeters is it on? So you could probably stop and think of some better ways to do that same kind of study now. One, obviously, you could have a robot drop the ruler. That would be a better method, a more consistent method. You wouldn't give anything away as the researcher dropping it. You could also have something easier to grab than a ruler. You could even do something more extreme with your method. What we do now is actually put people in MRI machines. Well, you can do it many ways, but one of the main ways we look to see what the brain is doing is we put people in MRI machines. We tell them when this line gets to this point on a screen because they're watching a screen as they're in the MRI machine. Or if you hear this sound, push the button. And so we will see their reaction time, both in the time it takes them to push the button, as well as what's going on in their brain. So again, all of those examples are science. It's the method that we're doing. So our methods have gotten better, tools have gotten better, and you'll see that as we go through this lecture today. So let's jump into our discussion of the scientific method. The main thing about the scientific method is that it makes sure that our results are empirical, or another way to say that is that there's some objective, tangible evidence behind them. So it's grounded in some sort of reality. We can observe this thing again and again and again, whether it is the inches on a ruler, whether it is a score on a survey, whether it is temperature, whether it is heart rate, whether it is a person's self-report of their happiness or something like that. And so that is what we're talking about, is studying things in an empirical way. It's really good also because then you can have other people test it in the same kind of way. The process of science is a cyclical process. We have an idea, a question, or we observe a phenomena, then we create hypotheses or test predictions about it. And we test that through these empirical processes that we'll talk about. Based on what we find, we draw conclusions, and then we evaluate those. So here's a diagram of that. It goes from those observations all the way to figuring out and doing a study and then deciding what to do based on our results. So the next point to discuss is a few key terms that we use in science that are not often understood by the general public. So most people use the word theory incorrectly. You might have heard someone in, say, an argument, maybe someone online, dismiss some point by saying, well, that's just a theory. So that's not actually how scientists use theory. So the definition of theory, I see my next slide coming up here is not the correct one. So I'm actually going to jump forward to the theory. So this down here is actually the definition of a theory. A theory is a broad idea or set of ideas that explain the data that we have and can predict future observations. So to have a theory, you already have to have quite a bit of information. You need a lot of data already, and this is your best big explanation of how this thing works. So an example of a theory is the theory of gravity. It incorporates all that we know about subatomic particles, mass, other forms of attraction like magnetic attraction and things like that. All of that is incorporated under the theory of gravity. Now, psychology theory might be the theory of attachment. So that incorporates everything we know about how a child attaches to a parent or a caregiver. And then also, more recently, we've done a lot more studies of how is attachment related to adulthood relationships, so partner relationships or other family relationships. So all of that are observations that we explain under this theory of attachment. So they're big, broad sets of ideas. Some are bigger and broader. They have more data. Some have a little bit less, but it's still a lot bigger idea than just one single idea. So as an example of this, I've got a few examples that we'll go through. But another point here is that a theory needs to be falsifiable. This means that it must be able to be proved false. So we have to state it or describe this theory, describe our observations or predictions in a way that you could actually test it. You could test the prediction and find that it would be false. So Freud's theories were big, broad explanations of people's behaviors, but they weren't actually falsifiable. So they were not good theories because he would shift them or move them. The theories always came after the fact, explaining away things versus making good testable predictions for the future or being able to test new observations. So a good example of this that hopefully will make sense is there used to be a theory called spontaneous generation. This was a theory for thousands of years, all the way from Aristotle's time, and it was the idea that matter simply generated from other nearby matter. So with that, an idea here is that dead wood would spawn or become mushrooms. So this was based on the observations they had. This was their big, broad idea, is spontaneous generation. So today I'm walking in the woods and I see a log, a dead, rotting log, and then I come back the next day and all of a sudden there are mushrooms there. How did that happen? Well, I don't have the tools to see more specifically, like a microscope, for example, but I observed that there was dead wood and today there's mushrooms. Maybe the wood became the mushrooms. You can also see this on, say, a ship. So I get on my ship. I have a bunch of grain on the ship so that we can make bread or whatever we're going to make during this course of this trip. And then a couple weeks into this trip, I see there's a lot less grain than there should be and a lot of mice, whereas before I didn't see like any mice. So my idea is based on spontaneous generation. This grain became the mice. And this was what a lot of people thought for thousands of years is how matter worked. And part of that, it was the theory based on their observations. This was the data they had. They explained and predicted what would happen based on their observations. So that was the theory of spontaneous generation. So it might sound kind of silly, but this was the broad idea or set of ideas. So it explained and predicted what they observed with their own eyes. So remember, theory is that broad idea, set of ideas. It has to be falsifiable. You have to be able to prove it false. So we did some studies in the past to falsify spontaneous generation. One is this one. It was first falsified, or at least we have record that it was first falsified, in 1668. So this was an idea for a very long time by Francisco Redi. Essentially, he said, I don't think spontaneous generation explains everything that we're observing with matter, so I'm going to do an experiment. I'm going to take one jar that's open to the air, I'm going to put some rotting meat in it, and I will watch and see what happens. This jar over here, my face might be covering it up for you. This jar over here, I'm going to seal it. So I'll put one jar open, one jar sealed, and pieces of rotting meat in both. And I think that this will help falsify the theory of spontaneous generation. I hypothesize that the one with the seal will not spawn or become maggots and flies. Turns out that's exactly what happened. The one that was open to the air had maggots and flies. The one that was sealed did not have maggots or flies. So everybody threw away spontaneous generation and we didn't use it anymore? Not exactly. It takes more than one crucial experiment or critical experiment to shift to a new theory, almost always. So with this, we didn't have an explanation of what was actually happening. We just had some observations saying, well, spontaneous generation doesn't explain this. If spontaneous generation is real, both the meat should have maggots, should have flies. But it's not working. It doesn't seem to work in this case. But it wasn't until many years later, so about 200 years, in 1859, Louis Pasteur was a person who boiled some meat broth and did basically the same experiment. Had some that were in these swan neck flasks, had some in sealed flasks, had some in open containers, and said, well, if spontaneous generation is real, all of these containers will get that weird film on it. So you might recognize the name Pasteur for pasteurizing. So this is when they realized things like germ theory and bacteria and microorganisms. And a big part of that was this kind of experiment, the series of experiments, and microscopes. So now they could actually see and observe more to understand and make a new theory about what was going on here. So we had a better view at the microscopic world now. We could actually explain that spontaneous generation was not a real thing. And that is that is when we finally shifted over away from spontaneous generation. So with that, it took between that 1668 and 1859, it takes more than one experiment. Another thing you might think is, well, the first scientist, Francisco Redi, does this study. Maybe a neighbor does that study too. But the problem is, some of their methods were not great. Maybe some of them had jars that didn't seal correctly. Maybe they had already contaminated the meat before they put it in, right? So because of the better tools, because of better methods, we had a much clearer understanding of the natural world. So let's look at an example of a actual theory in psychology. So this is part of Vygotsky's sociocultural theory. We'll talk about it more in detail later on, but the basic theory is that people learn from their cultural environment. People learn from others around them. Your culture will give you what's important in the place that you live. So this specific model here is called the zone of proximal development. It suggests that people can do certain things, and with the help of your social cultural environment, you can build your skills, but there are still going to be things you can't do. So you can think of this from an example of, say, skateboarding. So if you've never skateboarded, this can work for any kind of sport that you're learning, even driving a car. Like, you start with something you can do. If it's skateboarding, maybe all you can do is put one foot on the board. Maybe you can balance on it. Maybe you can even roll on it, right? For a car, maybe you only know where the gas and brake pedal are and how to read some of the dials. Maybe that's where you start. So for skateboarding, maybe with help of a friend who knows how to skateboard or a YouTube video, so your social cultural environment, you start to learn how to ride the skateboard. So you are learning within your zone of proximal development. Now, there's still things you can't do. You maybe can't do a jump with that. A jump on a skateboard is called an ollie. So maybe you still can't do that. Right? But as you are building this circle of what you can do expands into the area of what you can do with help, and that area of what you can do with help expands into this area of what you can't do. So you start to become more capable of doing more and learning more as time goes on. So maybe after a few days, you can learn with help how to do an ollie. Now that jump on the skateboard is within that circle of what you can do. But maybe you still can't do a kickflip. That's when you jump up with the board and flip the board around and land it on it again. So maybe you still can't do that, but someone helps you to learn some of the steps towards that, and eventually that is also within your circle of what you can do. So that's a current theory that is used in learning and education, but you should think for a little bit, what might possibly falsify this idea? So observational learning can happen here, socio-emotional learning, like people around us teaching us things. Are there any kind of learnings that don't quite fit? And there are a few types of things that don't quite fit. It seems like some people don't necessarily need specific training. There are rare stories of people just knowing how to do things without practicing beforehand, right? Or you could have something extreme like getting plugged into the Matrix to learn Kung Fu, right? So these kinds of things might suggest that there are other ways that we can learn. So what should we do with this theory? Should we try to revise the theory to add on to those things, or should there be a new, better theory? And that's one of the questions that scientists really grapple with. And we talk about at conferences and things. Should we go with a new theory, a better explanation? Should we modify? And that break to a new theory is a really critical part of any field of science. We saw this in physics. Hopefully you have a little bit of understanding. We went from like a Newtonian understanding of physics to Einstein and general relativity to more recently quantum mechanics. So there have been jumps and shifts of theory. The new theory always has to explain everything the old theory explained and all the new stuff that the old theory wasn't explaining well. And it can take time. Maybe it takes measurement tools and new technologies, right? We didn't get as far as we have in physics without things like particle accelerators, for example. So these kinds of tools can help us make those advancements, have a better understanding of our natural world, and same with psychology. Better measurement tools over time, like being able to use an MRI, help us have a much better idea and theories about how we learn. So, that theory is a broad set of ideas and it needs to be falsifiable. And this is different from a hypothesis. A hypothesis, I already mentioned it once earlier, maybe more than once, but a hypothesis is a testable idea or prediction. So, if my theory says that we can learn from other people helping us around us, like the zone of proximal development, I might say, okay, so I predict that if that theory is the case, I should be able to teach a 3-year-old math if they give them outside support. Like, I don't suspect that I'll be able to teach them calculus yet. That's probably too advanced. Like, they need to take other steps, is what the theory would say. But I should be able to teach a 3-year-old some math within their zone of proximal development. So I could test that. I could do an experiment, give a 53-year-olds a math test, put them in a room, no help, and give 50 other students a tutor. Each of them gets a tutor for math, then give them a math test. So every time you have a hypothesis, this testable statement come out well, every time that it does that, it gives more strength to the theory. It seems more likely that the theory is a good explanation of all of these things. So as more and more hypotheses are true that are predicted by the theory, that theory gains more credibility. And it's added to that body of explanation of what this theory is explaining. But the hypothesis is that testable idea. Generally, you'll have a single study that tests a single hypothesis, or you might have a study that tests like 3 or 4 hypotheses at the same time. From those results, you might start to think about the broader theory, but usually any given study is testing a couple specific hypotheses. So it's a little bit of a cycle. You've got a theory with observations and predictions. You make hypotheses, you test them out, you add those to your observations, you either modify or don't modify the theory, or you have to come up with a new, better theory that explains it better. So another component of science and the scientific method are these 4 key things. We need the studies to be fair, so we need to include all the relevant data when evaluating hypotheses. This is one thing that we've unfortunately seen recently give a bad view to psychology, is that a lot of older studies of people who have recently been passing away have been gone through. The data has been looked through, that's been like saved in boxes in basements of universities. And we're seeing that in some cases, they didn't include some data that would have made some of our later advancements a lot easier. Basically, things that looked pretty clear based on the data that they published in future studies that tried to replicate it and tried to get to the bottom of these phenomena, things like bystander behavior, for example, and the bystander effect. We've seen a lot of studies more recently that it doesn't seem to be happening as often as original studies would have claimed. A lot of those original studies didn't include all the data in them. In reality, a lot more people help than the bystander effect might make us believe. It is a good story to kind of sell, like, hey, we need to study why people don't help. And people don't help sometimes, right? But there are a lot more situations where people do help. So that helps science be better, and that makes a field look better when it is being fair and including all the data that you need. It also needs to be falsifiable, so both theories and hypotheses. So hypotheses should be every time falsifiable. That's basically the point of your study, to see if your hypothesis turns out or not. And then theories, overall, like we just talked about, should also be falsifiable. Predictability. You should be able to explain things well enough that you can predict something else happening. Right? We can predict when the aurora will be above us and we might get the northern lights down here in Washington. So you need to have that kind of predictability. Your theory has to explain things enough that you can predict. So we have that in psychology. We know enough about early childhood development that we can predict what might happen given a risk factor or a protective factor. So verifiability, we also want other researchers to verify and replicate the research. So there's a lot of methods that you can do to do that. One is peer review, like peer-reviewed research. Give a original paper to other people in the field, see if they think it looks like you're being fishy, see if it looks like you're going beyond your results, see if it looks like you did the appropriate kind of tests for the data that you had, that kind of thing. But also you can replicate studies as well. Just redo it. Maybe do it just slightly different. If you tested in a sample in this one state, maybe test again countrywide. If you've tested in the US, maybe now test multiple samples worldwide. So replication with a slight change to understand more. All right, another big thing is empirical testing. We need to test things empirically and scientifically, and essentially one of the big pieces of that is our operational definition. An operational definition is a fancy way to say the way we are measuring a variable. So a variable can be anything, anything that varies in human experience, in geology, anything that varies in geology, right? So for humans, height is a variable, weight is a variable, gender is a variable, um, happiness is a variable. Happiness can vary. Purpose in life, heroism, pro-social behavior, just about anything you could think of in human experience varies between people. And so any of those things could be a variable. But how are you measuring that thing? How are you measuring heroism? How are you measuring purpose in life? How are you measuring happiness? How are you measuring height? Are you using centimeters? Are you using inches, right? So how would we operationalize happiness? Take a minute, write down a couple ideas, like pause the video right now, write down a couple ideas of how you would operationalize happiness, how you would measure it, and see if it's similar to some of the ways that we actually do. So some of the ways that we actually do measure happiness, we have used observational studies, watching and seeing if people appear happy, maybe with smiles or something like that. But that's not necessarily the best method because if you're, say, measuring smiles, even looking at behavior, people can pretend, right? They can act. An actor might not be happy at all, but might be acting very happy because they're an actor, right? So if you did something literally like this picture and actually measured someone's face, that would actually not be a good idea either because people's faces are different, different sizes, different shapes. Some people might be very happy, but their smile doesn't go as far as another person who's maybe not as happy. So there are limitations with each of our measurement tools. But looking at behavior isn't a bad way to look at happiness of a group. One way that we often use is surveys. So you might give a child like these pictures and say, how happy are you from this one to this one? And let them pick a face that they'll probably understand. Or if you're doing this with someone who doesn't speak English, right? You can use some images. You could ask someone who knows how to read, where would you put your happiness here on this scale? And they might mark somewhere on it, right? So that is a way to get at someone's happiness. Again, in a survey, people can lie. So you would need to test and make it so your survey is resistant to that. That you can either tell that people are lying or that it's less likely because of the ways that you structure the survey and ask the questions, making sure it's anonymous, things like that, that people are less likely to lie. One example of that that's pretty funny of how we can catch some people lying is there's a lot of studies of both adolescent sexual behavior and adolescent drug use. So one way that we figure out if adolescents are lying on the drug scales is we list a bunch of different drugs, like and a bunch of different names for the various drugs that people use. And in those names, we also have researchers just make up names of drugs that don't exist. Obviously, they've got to make sure that these drug names don't actually exist, but they put those fake names in there. And so if you have someone say that they are using all the drugs or that they're using quite a few and then also the ones that aren't really drugs, you can be pretty sure that that person's lying and throw that data out because it's not actually valid. So, just one funny example. Another way that we measure happiness, and some of my colleagues actually did this, was using skin swabs. You could use like blood samples, but that's a little more time consuming, a little more invasive. You can have participants on their own with like a pre-packaged skin swab, swap the inside of their mouth, and mail it into a lab. So I did have a colleague who did that as part of their study, which is pretty neat, as an additional measure of happiness. They had their survey and they also had that. They actually got a few survey questions multiple times a day to just their phone in little app messages, which was pretty neat. All right, so that is operational definition. How do you measure? How do you measure happiness? That is what the operational definition is. Another big part of empirical testing is analyzing the data. Now that you've got your data, whether it's from an interview, whether it's from a skin swab, like a skin cell swab, if you've got a survey data, whether you've been making observations, you need to analyze that and then do those analyses to see if you have a result. So a key point in analyzing data is inferential statistics. The key word here is infer. So we are inferring things about people based on our results. So let's say this right here is called a normal distribution. You might have heard it called the bell curve. In reality, this is just an example of how the normal distribution is. But let's pretend that this is actually our, oh goodness, why did I just forget the type of graph this is? Uh, it's fine. Histogram. Our histogram, because you would have like categories under here, is actually the happiness of people. So this would be like not happy at all. This would be very, very happy. Let's say most people fell in the middle of our very happy thing. So we could have that data, and then after we know that people are on average right in the middle. All right, that's what this would say. Then we can do a new test. We could say, all right, I'm going to put these people who are average happiness right now, I'm going to put them all in a room with puppies and see how happy they are. So I put them all in a room with puppies, and then I check their happiness again, and maybe this distribution is kind of a lump over here with some people don't like puppies, maybe some people are even scared of puppies. So you'll have maybe a big group over here and then a little group over here. That would no longer be a normal distribution, but just as an example. So you analyze that data, and then based on that, if you see most of your group, most of your sample got happy with puppies, you might infer, hey, anytime I put people in a room with puppies, they'll get happier. I am now inferring things about people. Now, if you only tested a specific subset of people, so maybe an ethnicity or one gender or one religion, you might have some effect based on those variables. Probably not those for this example, but if you had somehow had all people who either were or were not afraid of dogs, that might have an actual effect, right? That would be a variable that would have an effect. So your inference isn't always going to be perfectly true, right? But it's kind of your data-driven best guess based on actual hard data. All right. And then based on your data, you then draw conclusions. After your stats, you think, is your hypothesis supported? If I hypothesize people would be happy with puppies, is that hypothesis supported? And then do those results alter the original theory? Again, usually that's not the case. Usually you need more and many, many studies to then alter a theory, modify it, or jump to a new theory. But you should ask, can we trust the conclusions or the methods? Right? If I happened to have everybody in my sample who was afraid of dogs and I put them in a room with puppies and they were all terrified rather than happy, so they all rated themselves very unhappy, can I trust those conclusions to infer it to the general population? Probably not, right? So that goes to this last one. I didn't use good methods in picking my sample. So who can we generalize the findings to? Well, you could probably if you did use a sample of people who are afraid of dogs and all of them hated being in a room with dogs, well, you can probably generalize those findings to people who are afraid of dogs. You probably can't generalize those findings to people who love dogs, right? So depending on your sample, this is why we talked about weird samples in a previous class. Weird being white, educated, industrialized countries, rich and democratic. I think I got all the letters in the acronym. If that is your sample, you might not be able to generalize to, say, a teenager in Brazil or a native Alaskan or a person in rural China, right? So there are other people with other cultures and upbringings that, based on whatever your study was, you might not be able to generalize to them. Some things you can. Like one thing that we found, because we've studied people from all over the world, is that our brain structures for most people are basically in the same spot. Like the prefrontal cortex does higher order thinking, it's up here in the front. Language is pretty much for everybody on the left side of your brain, right about here. So no matter where we go in the world, that specific thing is the same. Unless someone gets like an injury or something like that, then the brain can actually put those functions in other places in the brain, which is pretty cool. That's called plasticity. But yeah, we only know that because we studied. We had to check before we generalized, right? And now we can say, hey, if I grab a person from here in the US versus a person from Brazil and look at their brains, if I'm just looking at their brain, won't be able to tell the difference, right? All right, now we have those conclusions. We can do some steps in evaluating those conclusions. One thing that we can do is called replication. Replication is when other researchers do the same or nearly the same test. So if I found something that worked for adolescents in California, maybe I have a colleague in Florida do the same kind of test and see if it works there too. That's a replication. Another thing you could do is make, and often scientists actually do this, make slight adjustments. So it worked for these people in California that were this specific age range and this specific ethnic breakdown. I can do it in a couple other states and add a few more ethnicities or expand the age range or something like that. So add something a little bit new so you're replicating and adding onto it, because actually like that new different thing is easier to get published in journals. So often our replications are slight variations to learn a little bit more, which is good. Another thing is evaluate the theory. Do we need to change the theory? Do we need to adjust the theory? Do we need to jump to a new theory? Usually, again, it's not going to happen from one single study. Peer review is another big way that we evaluate our conclusions. You have the peers look over the research, look for technical errors, make sure you're not going beyond your conclusions, make sure you didn't miss some big background thing that you should have known before you did your study. There was recently, I published a research paper. I mean, now it was like a year and a half ago, but I published the paper, and then the next month I'm like searching for research again because I do that regularly to see what's new. And I learn that a few weeks before I published my paper, a paper was published that was on the exact same topic. It wasn't like I definitely should have cited that paper. I should have included it in my references. It would have helped a lot of the points I ended up making. Because of my conclusions, I should have known it beforehand, but I searched after I had sent it into the journal editor. So, what are you going to do? But none of the peer review, well, actually, it had been through peer review already before this paper came out. And it was in the limbo time after it's been accepted, but it's not actually published yet. So, or I forget exactly what the order is. If I had read it, I would have been able to still make adjustments to the paper, but I think it had already been peer reviewed. But if I had done that, it also would have gone back to the peer reviewers. Anyway, that is a whole long convoluted way to say peer review is a really good way to make sure good science is coming out. Another thing is meta-analyses. Meta-analyses are a really fantastic way to put multiple studies together. So as we're doing research papers, we're looking at research, we're interpreting it, we're putting it together like in our own brains with the concepts. A meta-analysis actually takes the results and data of other studies, puts that together. So if you have, let's say, 10 studies of whatever it is, let's say 10 studies of mindfulness. You have a new mindfulness exercise and you're testing it out, and other people are testing it out across the country independently, and you don't actually know about it. They all publish papers on it. You can do a meta-analysis taking all of the study's data, put it together, and have a much clearer result of what's actually happening in the world, which is pretty neat. So with this, hopefully with this pattern, we are solving problems. So the goal is to solve problems with applied psychology. So you take your socially significant problem, you do some research to see what's been done, you get out in the real world, you talk to practitioners. Let's say you're trying to solve poverty. So you talk to people working on that, you look at what's been done before, you use this theory and research methods to design some new studies, you test things out, you test some interventions out, you see what works, then you disseminate or give that to lots of audiences, whether it's evaluators, whether it's policymakers or other researchers. You do this cycle until you solve the problems. So that is really the model of what we're trying to do in science, to build research and build answers and understand how to solve problems. All right, so let's talk about a couple types of research: descriptive, correlational, and experimental. Descriptive is pretty easy to understand. You're describing a phenomenon. You don't try to prove causation here. Some examples of this are just doing observations. Surveys can be descriptive. You can use surveys in experiments as well. Interviews, case studies, and content analyses. Content analysis is basically taking already written content and analyzing it for things like themes. So if you want to look at the most recent election cycle, you could get a transcript of like all of news coverage, which would be a massive amount of data. But a content analysis program could do this, and it would tell you what are the most common themes coming out, that kind of thing. And that could help you understand something about a topic. So case study is a specific study of a unique feature, whether it's an individual with some unique disease or a school district who's doing something very different. It's a unique case. Right. So correlational research is one that you'll come across a lot as you read research in psychology. And correlation, when you see that word, think about relationships. Relation, correlation. So it's all about relationships between variables. So again, variables are anything that varies. Height and weight are correlated. On average, for most people, if you're a little taller, you're a little heavier as well. Right? So that's a relationship between those two variables. This being said, a key point that I want to bring up now, and I'll emphasize in a moment: correlation does not mean causation. So just because there's a relationship does not mean one of those variables causes the other variable, or vice versa. So when we write correlations, they range from -1 to +1, and 1 being the strongest. Either negative or +1 is the strongest relationship, a perfect relationship between the two variables. So how close it is to 1 tells us how strong it is. And then if it's closer to 0, if it is 0, that means the computer can find no relationship between the variables. You can do correlations by hand. When I learned stats in grad school, I had to do that my first like 2 years. Maybe it was only 1 year. It felt like 2 years. You can run correlations by hand. It's just equations, series of equations. But the closer it is to 0, that means there is no relationship between the variables. So here's a couple examples. Here is a negative correlation. You know that because it goes down. So the negative is not like a bad thing, and the positive is not a good thing. The negative and positive is just math talk. So negative means the graph is going this way. Positive means the graph is going this way. And so this is a strong positive correlation. This is a pretty strong negative correlation. So both, this one looks a lot more narrow. So that would probably be like 0.92. So very close to +1. This one is a little more spread out than this one. So this would probably be -0.72. I'm just making these numbers up based on this. And that is still a very strong negative correlation. This one down here is a good example of no correlation. As one variable goes up, there's no relationship with the other variable. Here, one variable goes up while the other variable goes down. Here, one variable goes up and the other variable goes up at the same time. So let's look at a couple examples. Some of these might be causal relationships, so I don't want it to be too confusing, but hopefully these examples help. So let's look at this one with no correlation first. This variable is the test grade. So we're testing people, maybe we give them the midterm exam. And we get the variable of how much milk they drink. Maybe it's how much milk they drank that day or maybe that week. So test grade is up here. So people who scored high on the test up here, low on the test down here. And we compare it to the amount of milk they drank. Here we see there is no pattern. There's no relationship between the amount of milk they drank and their test grade. Kind of random variables to each other. But over here, we see one that might have some causal relationship, but again, correlation does not mean causation. And I'll show a good example of that in a second. So here is test grade again, so high test grade, low test grade, and this is number of parties. So not very many parties, lots of parties. So you see, the people who went to lots of parties, they also tended to have the lowest test grade. People who attended the least parties had the highest test grade. So again, this is a negative correlation. It goes down that way. Here's a positive correlation. This is hours of studying, so kind of opposite of that one. So few hours of studying, lots of hours of studying. So those who studied very little got a lower test grade. Those who studied higher got a higher test grade. So these are probably causally related right there. But just because these ones are, not all correlations are causally related. So as a good example of that, this is an actual result that we've seen in data. There is a strong positive correlation between ice cream sales and violent crime. So this isn't actually the graph for it. It's not this strong of a relationship, but this is just a visual example. So this, we could say this is ice cream sales. So on days when there are lots of ice creams sold, there is a lot of violent crime. So down here we've got violent crime. On the left side we've got ice cream sales. When there's not very many ice creams sold, there's not very many violent crimes. And when there's a medium number of violent crimes, there's a medium number of ice creams sold. So what's happening here? Take a minute to think about why this might be. Are violent criminals doing violent crimes, and then every time they do a violent crime, they really want some ice cream? If people are hearing about violent crimes, does that make them really want ice cream? Is eating ice cream causing people to go commit violent crimes? Sounds like it would be a plot in Despicable Me. That's not a bad idea for a story. To have ice cream that makes people go and commit crime. But no, right? These are not actually causally related. There is a relationship between these variables. They're definitely related to one another, and we can graph and map this connection. They're related, but one is not causing the other. The ice cream is not causing the violent crime. The violent crime is not causing the ice cream sales. They are correlated. They are related to one another, and correlation does not mean causation. So in this case, the other variable is heat. Days when it's hotter, more ice creams get sold. Days when it's colder, fewer ice creams get cold. Days when it's hotter, more people are out. More people, we've seen a pattern of more people tend to be more aggressive and do more violent crimes when it's warm out than when it's cold out. So I had my first job was actually working in basically an ice cream shop. It was frozen custard, which in my opinion is way better than ice cream. I worked in a frozen custard shop, and I started in the fall, and then it got to be the winter. I was in a place in Indiana where that was very snowy. So it was always a lot of fun to do my whole shift in the winter, and I'd get maybe one or two people. Then when it got to be summer, it wasn't quite as fun working there when I had a line out the door of customers and I didn't know how in the world I was going to get all this work done with the employees that were there. So there's a lot more people buying ice cream. Luckily, I didn't have the experience of the connection between ice cream and violent crime at the same place. So another type of research, aside from correlations, is longitudinal research. Longitudinal research is a key piece, and you can see this word right here, long. It takes a long time to do longitudinal research because you're following the same group for a long period of time. Technically, you could follow the same group for like 5 days after some intervention and measure them every day, and that would also be longitudinal. It just needs 3 or more measurements over time. But usually when we're talking about longitudinal, we're talking about months long, years long, decades long studying. So longitudinal, you are taking the same group of people, following them over time. And it's really fantastic for developmental research. We can track how does memory work when a person is 1 versus 100. We can follow them longitudinally. So this graph here is actually looking at cognitive capacities of people at their different ages. So it's looking at inductive, hopefully the video capture is getting this. This is inductive reasoning, spatial orientation, perceptual speed, numeric ability, verbal memory. And we've got different ages. It starts at 25, and they followed these people all the way till they were dead. But the last time on this graph is when they were 88. and it was like 360 or something people. And when they were 88, there was still like 260 of them around. So it was a pretty big group that they measured these cognitive capacities for over their life. So pause the video right now. Write down a couple observations that you have. What does this data tell you about cognition or specific cognitive capacities or aging in general and cognition? All right, hopefully you've done that. I'll point out a couple things. One of these things that drops off the steepest here is numeric ability. Why might that be? Well, numeric ability is probably not being used very much by these people. They're not needing to learn new things with numbers, use them in different ways, so they have their skills and then they stop using them as they get into their 60s and 70s and they lose those skills. Versus here we've got the square with a plus is verbal ability. Well, there's if people are still using that cognitive skill of speaking with people, having conversations, that kind of thing, it drops off a lot slower. Another interesting point here is that while we can measure this as scientists, we can measure the drop from here to here. Look at the scale of the graph over here on the left. The top end is 55 and the low end is 35. It's not even going down to zero right here. So this drop, while it looks kind of dramatic right here, the drop from here when they're 60 to 75, that can be measured by a scientist, but as a person, just going through life, you would not notice this drop in your cognitive ability. A partner or a friend or a grandchild probably wouldn't notice this drop in cognitive ability. You'd see basically no difference from this drop. It's not until you get a drop down to here or here that other people around you or even you yourself will start to recognize that. So this tells us a couple things. This tells us that cognitive capacity remains stable a lot longer than people previously believed it to be. It also shows us that for those things that people are using, they're keeping those skills longer. There was also a subgroup of people that in this study, they actually started doing cognitive training. Basically, they had a family doctor say, hey, you should do something like play Sudoku or play chess or learn new hobbies or read books to work on your brain. And for those people who were doing things specifically for their cognitive health stayed the same or went up. So at any point of your life, you can increase your cognitive capacities, abilities, as long as you don't have a neurodegenerative illness. So that's the only caveat there. All people are capable of upping their cognitive capacities anytime in their life. Going to college classes is a really great way to boost your cognitive capacities, your memory, your perceptual speed, your verbal ability, all of these things, your inductive reasoning. So longitudinal studies are really great ones to see change over time. Before this time, we thought that people lost cognitive capacities much, much earlier. It wasn't until these kinds of studies that we saw, hey, actually, people keep their cognitive capacities for a lot longer than we previously thought, which I think is a very hopeful and good thing. Another important type of study is the experiment. And an experiment's really important because it is the only type of study that can determine cause. Technically, you can get at cause with good longitudinal studies as well, but for simplicity's sake, let's stay focused on some simple experiments. Simple experiments can determine cause. So while we said correlation does not equal causation, cause is the exclusive focus of an experiment. So to be an experiment, you need a couple things. You need at least two variables, and you need to manipulate at least one of those variables to see if it causes a change in the other variable. So a simple example of this is here in the picture. We've got students taking a test. So we've got two groups of them. So we've got the test is one variable, and that is their score on the test. And the other variable here, the second variable, the one we are manipulating, is the sound in the room. The control group gets a quiet room. The experimental group gets a brass band playing while they do the test. So what would your hypothesis be for who would do better? The group that was in the quiet room or the group in the brass band room? My hypothesis would be that the quiet room, they would do better on the test. So I have two variables, test and the sound in the room, and I can manipulate the sound in the room. And based on that manipulation of the sound, I can see, did that sound cause a change in the test score? So here we've got an independent variable and a dependent variable. An independent variable, I'll also call it an IV, is the variable that the experimenter manipulates or changes. So in this case, it was the sound. Is it a quiet room? Is it a loud room? We could do a different kind of an experiment where we try different kinds of music. We could have a loud brass band. We could have another room where we have quiet music playing, and then a room that's completely silent. So we could test that as an independent variable, but still use the same dependent variable of test score. So the dependent variable, you could think of it as your final measured variable. You want to see if this one changes. You want to see if it changed dependent on the independent variable. So independent variable, you manipulate and you see if it changes the dependent variable. You could have more than one dependent variable. Let's say, same kind of example, we've got the quiet room, loud room, taking a test. You could have a second dependent variable of an anxiety test too. You could have them answer a survey about their stress level. So, and then you might have a hypothesis. You might hypothesize about both those dependent variables. I hypothesize that those in the loud room will have higher stress and have lower test scores. I hypothesize that those in the quiet room will have higher test scores and lower stress. So that's two dependent variables, even though we're manipulating one. So for an experiment, you need at least two variables. You can have more, but you need to manipulate at least one of them and see if it causes a change. So with this, the better thing than just taking one classroom of students and splitting them up, if you see here in this picture, there's what, 4 students in each group. It's not a big group of students. It's best when you have even more in the groups to get a better sense and infer more about the population. But essentially what we want to do is randomly assign into the groups. So here, random assignment is when you take your sample and then you randomly put them in the treatment or control group. And these orange and purple people represent any individual differences that could potentially affect the test. Maybe the orange people studied more and the purple people studied less. That could possibly impact their score on the test, no matter what the quiet and loud room is. We wouldn't want everybody in the loud room who studied more for the test and everybody in the quiet room who didn't study for the test, because that might mess up our results. We wouldn't be able to see that the loud room is making them do worse, because they might still have a higher score because they were the ones that were studying. So to get rid of all those potential differences, even ones that we don't even know of, one that we haven't even mentioned that could possibly affect them is maybe the orange people are all people who slept better the last night. And so they might do better on the test because of that. And the purple people didn't sleep well last night, so they're going to do worse on the test. All of those possible differences, we can spread them out equally by randomly assigning to our groups. It will be better if we don't just have 6 people in our sample, but if we have, say, 600, we can randomly assign them to our 2 groups, right? And that will get a much better, clearer picture of how people will behave on average. So hopefully in both the treatment and control group, with 600 people split into groups of 300, we would have one person in the group who studied and slept and ate well the night before. And in the control group, someone who studied, slept, and ate well the night before. So that's what we want. And then also we want in the treatment group someone who didn't study, who didn't sleep well, and didn't eat. And we want that in the control group too. So both groups want someone who didn't sleep, didn't eat, and didn't study. Right? We want those individual differences spread throughout both groups at about even rate. So you could think of the orange and purple people as different ethnicities split equally, a variety of genders split between the groups. You could think of it as IQs split through the groups. You could think of it as personality types split evenly through the groups. So that's why random assignment or random sampling is really good. Random sampling is similar. It's that the whole population, you can pull from the whole population. So randomization really reduces the likelihood that your results come from some difference that's already there, like they studied or they didn't study. And that lets you see, did your change, did your manipulation of your IV, did that cause a change? Right. So that's an experiment. It's a very important thing because we can see cause with it. All right, when we are measuring things, when we are doing studies, another important piece is reliability. So when you hear reliability, think consistency or replicability. Is the measure that we are using, is it producing stable, consistent results? With that, is the survey acting the same way each time we use it? If we give them the survey this week, will it be the same as when we give it to them next week? Something that you don't expect to change very quickly, like maybe personality style, that should probably be the same this week and next week. Something like happiness is a state, is more fleeting. Um, so you might expect that to change more dramatically. But some things we want them to be very reliable. So some examples of this are this scale and this thermometer. These ones look pretty reliable. I would probably trust them. These ones look unreliable. It looks like when I put it in my mouth when I have a fever, it might give me a temperature of 110 degrees, which is not very true. That would mean I was dead. And then if I try it again, it might give me a rating of 60 degrees, which again is not great. I would be dead, but that time frozen. So this is an unreliable measure. This is an unreliable scale. If you step on your bathroom scale and you get a number, and then you step off it and then you step back onto it, and now the weight is 15 pounds higher, are you going to trust that scale? Probably not, right? It's not being reliable. It is not being consistent. So in psychology, when we're using surveys or other kinds of measures, often with surveys especially, we use a lot of reliability testing to make sure that we are being consistent with our questions. So with this, we do test retest reliability. We do a test today. We do the same test next week, see if you're getting the same answer. Internal consistency is basically you test the questions against each other. Each question should be getting at about the same kind of thing. So you kind of split it in half in different variations and make sure both halves are saying the same thing. And then inter-rater reliability is if you have observers. If we've got like three people watching the same situation, observing sharing behavior in children or something like that, all three of us should agree and rate the same thing with very little variation. So that is some ways we test reliability. And with that, we come to validity. Validity is synonymous with truth or accuracy. So are the conclusions, are they sound? So can we attribute the results to our experiment or some outside force? Were the results because we had them in a quiet or loud room, or was it actually because everyone who studied the night before was in the quiet room? So can we actually attribute the answer to the study? Also, is the measure we're using, is it actually measuring what it's supposed to measure? So are we using a smile and the length of your smile for happiness? Or are we using like a survey and hormone levels? That would probably be a much more valid measure of happiness. So another example of this scale, and we'll talk about why IQ and having just like a single number is bad and how IQ tests are really central to what people think is important about them and how IQ tests are really problematic overall, and some better ways that we do IQ tests, like solving puzzles to see if you are good at the cognitive skill of solving puzzles rather than like IQ. Anyway, the point is, if I wanted to say get your IQ score, I could put your head on the scale. Maybe you lie down on a table, a doctor's bench, you lie your head on the scale, and I get a number. Let's say it's 8.5 is the number that's on the scale. So I tell you, all right, your IQ score is 8.5. Next person comes in, they put their head on the scale, they get an 8.9. Say, oh, you've got a higher IQ. Your IQ is 8.9. You've got a higher IQ than that person. So this is a reliable measure. When you come back and try to repeat this and you put your head on that scale, you will probably get a consistent result of that 8.5 or whatever it was that I said in the beginning. But is that a valid or a true measure of your intelligence? Well, clearly not. It's a valid measure of the weight of your head, which I think heads on average are like 8 point something pounds. But no, that's not your intelligence, right? So that is not a valid measure of intelligence. So first, you need something to be reliable. You need to make sure you are consistently measuring the same thing. And then you've got to make sure that thing you're measuring is actually what you want to be measuring. So if you think you're measuring happiness, you want to make sure you are actually measuring happiness. If you think you are measuring personality, you got to be sure you're actually measuring personality. And so a psychologist who is creating, say, a survey would do a variety of tests to prove that that their survey is reliable and valid. It's a very important piece when creating an MRI machine. Studies had to show that it would reliably give the same kind of result for scanning, and they would scan things that were more simple, even in the beginning, to make sure it was being consistent. Then they would look at validity. Will it give us a true, accurate representation of what's happening in someone's head? So they would test both reliability and validity. Any kind of tool that we use in science to measure and get data needs to be both reliable first and then validity. You can't have validity if you don't have reliability. If it's already kind of broken, giving you really weird readings each time you step on the scale, step off, step back on, it's 15 pounds different, then you can't trust its validity because it's not reliable. So reliability first, then validity is kind of the key essential piece that makes sure you're measuring what you want to be measuring. All right, another big feature in studying is bias. There can be experimenter bias, there can be participant bias as well. So participants sometimes think that they know how you want them to act, and so they will act in a different way. In psychology, we want people to act as they would. We don't want them to pretend in some way. We don't want them to act in a socially desirable way. We want them to act and think as they would, so we can understand how they are. Experimenter bias is when the experimenter affects the study in some way. A good example of this would be, let's say I had a treatment that I'd been working for a long time on. I thought this was really great and it would really help people. When I give that to people, I might talk to them, be very excited about it, be more engaged with them, follow up more often. And then for the people in the control group who get a placebo, I might give it to them and be like, okay, give your reporting. Just those simple behaviors that are different might lead to different results. People might be more excited or have a better belief and have more placebo effect based on the treatment I'm really excited for. Right? So my bias can change the study. So that's why double-blind studies are a thing. And that is why we have a bunch of other ways to make sure that the experimenter is not biasing studies. So a really funny example of this is actually the story of Clever Hans the horse. So this was a horse that could do math. Essentially, there was this board here, and the owner of the horse would take money from people, and when they paid, they could ask the horse a math question. So when you ask the horse a math question, it would clomp its hoofs. It would say, "Horse, Hans, do 2 plus 2." And it would go clomp, 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 clomp. 4 clomps. And with that, it would be like, wow, amazing, the horse can do math. So someone else would ask a math question. They would pay the person and ask a math question, and the horse would clomp the answer. Let's say it was 9 divided by 3. The horse would clomp 1, 2, 3 times. So hopefully I did my math right there. So it seemed like this horse could do math. Well, spoiler alert, horses cannot do math. So consider for a minute, like pause the video, think about what might actually be happening here. Why is this horse usually getting the math questions right? So pause and write down a couple of your ideas. So when researchers tested this out, because they wanted to see, well, why is this horse able to do math? It was a case study, a unique case of a horse being able to do math. So they did things like remove the owner, like keeping the owner away, out of view, even out of earshot of the horse, because maybe the owner's signaling some way. They also moved away the crowd, had fewer people in the crowd. They did new questions that the horse probably wouldn't have heard before, all sorts of different things. And what they noticed was when the crowd was smaller or really far away, the horse would get the questions wrong way more often. And this is because the horse had actually been trained to follow people's body language. When a whole group is surrounding this horse, they will collectively act in a specific way. As the horse gets closer and closer to the answer, they'll kind of be tense, maybe a little quieter, and have observable behaviors that the horse would recognize and stop clomping. And then it would get its treat, its carrot, whatever it was. So the horse knew, watch body language, when people act like this, stops clomping, which is really impressive for a horse. Like good training to get the horse to observe that kind of behavior and act that way. But it's not quite as impressive as a horse doing math. Dogs that are used as service animals do a lot more amazing tricks than that. I say tricks, a lot more helpful, useful things that they're trying to do. Laundry, getting food, getting people's medicine, dialing, like using buttons to dial numbers on a phone. It's really impressive. But yeah, very impressive horse. Couldn't do math. And this kind of is an example of experimenter bias. In this sense, the experimenters are the people. They are giving bias to the horse. They are telling the horse what to do unintentionally. And so we have to solve these problems by doing things like using placebos and double-blind experiments. So placebos are fake treatments so that people don't know that they're in the control group. And double-blind is when the researcher and participant don't know which one they're in. So with this, all of these types of research, no one is better or worse than the other. Each of these types of research are useful. Descriptive research, correlational research, and experimental research. Experimental and longitudinal research, it's not listed here, but it's important too. So all of these, none are better or worse, each have positives and negatives. Some things you really can't do an experiment on, right? So we couldn't say, let's say we wanted to see the effect of some chemical on pregnancy and the outcomes of birth. If we think it's a harmful chemical, we can't like run an experiment and say, hey, you 50 women who are pregnant, or you 50 pregnant people, you take this chemical that we think might be harmful, and then you 50 pregnant people, you don't take this chemical, and we're going to see what happens. Obviously, that's not ethical. That being said, some really terrible studies have been done kind of with that same basic idea, giving people specific diseases and infections without any informed consent in the past. But that's one reason we have so many ethical rules in research now, which we'll get to in just a couple minutes. Before we get to that, though, let's talk about populations. So a population is the entire group of people that you're interested in. So we might say all the students at Olympic College, that is a population. The population of the students of Olympic College is every single student that's in Olympic College. You could also say all students in a gen ed course. So that would be a subset of that population. So the population is the entire group. You could think of the population of the world is every single human on the face of the planet. The population of the United States of America is however many people are in the United States of America. So that's the entire population. You could think of the entire population of the state of Washington or a particular county that you're in. So that's the entire group. Usually we don't have access to the entire population when we are doing our studies, so we use samples. We use subsets of that population. So I could get, if I wanted to look at all students in Olympic College, I might be able to access that population, but I could also get like 2 students from every single class at Olympic College. That would give me a pretty good sample. That would be, I probably should have looked up before doing this recording how many students are in Olympic College. I saw the data a couple weeks ago of how many were there right now, but that's probably not accurate too whenever you're watching this either. So anyway, the whole population is all students at Olympic College. A sample is the collection. I could say, look at the whole directory of all students at Olympic College and tell a computer, hey, give me 200 people from this list. And that would be a sample of the whole population of students at Olympic College. So that is how we get most of the groups that we study, is by sampling. Now with this, a random sample is better. So a random sample is when every single person in the group has an equal possibility to be selected. That's a really good thing because then I will hopefully, especially with a big sample, so let's say let's pretend we've got a whole population of 10,000 people. If I sample 10% of that, what would that be? 10,000, 10%. That'd be 1,000 people. Perfect. Easy math. So I now have 1,000 people, and each of those 1,000 people had an equal chance of being selected. That's random sampling. It's similar to random assignment, except you're pulling from the population at random. So hopefully with your sample of 1,000, you have a bunch of people that demonstrate the variety of the people in your population. So for example, if I wanted to look at the population of the United States of America, I wouldn't only include people from King County, Washington. right? There's a fair mix. There's a pretty good mix of ethnicities in that county, but it would probably be better to pull people from all over the country. People from Florida, Georgia, New York, Chicago, Kentucky, New Mexico, Arizona, California. Maybe you could take proportional to the state size. You could take like a half of a percent of the population as your sample. That would give you a ton of people and a lot of variety. So random sample is always better. You're not always able to do a random sample. In a lot of psych studies, we have volunteers doing the study. And so at the basic point, the people who are doing the study are the people who would volunteer to do a study. So that's a different population than a random sample in and of itself. So a random sample should, if it's big enough, resemble the population. So if we get, let's just make it easy, 400 people from every single state in the U.S., that should be a pretty good resemblance to the population of the United States of America. Pretty similar gender breakdown, ethnicity breakdown, religion breakdown, age breakdown, that kind of thing. All right, so with this, another thing is the settings that we do research in. Naturalistic observation is when you try to observe people in the most natural setting that you can. So you might observe students in a classroom. You might observe students on a playground. You might observe college students in a coffee shop near the campus. With this, you can't control for things like you can in experiments, but you are not likely to change behaviors. If you're just sitting on your computer in a corner of a coffee shop, nobody thinks that's out of place, right? So their behavior will probably not be changed by you being there observing. So with that being said, another example of observation is a laboratory setting. So this is usually going to give you more control over variables. You can set up specific scenarios. There was one pro-social behavior and heroism study that actually, like during the course of a group working on something, they pumped like a smoke machine into the room to make it look like a fire was happening, that kind of thing. So you can control variables and observe what happens. It gives you more focus on the variables, but because usually in this kind of setting, people know they are being watched and they're being observed for a study, so they might change their behavior accordingly. They might act a little better or a little worse or a little different because they are being observed and they know that. So you've got to weigh those trade-offs. So we kind of alluded to this earlier, but another point in research is distributional thinking. This goes with our inferential statistics. We look at the distribution that we find in our data, and then we look for norms or things that are the most common. So we look at the averages, the medians, the means, and we build that data from our samples. So our samples give us ideas about the whole population. So as an example, this is the breakdown of heights. So it's kind of hard to read, but heights in inches for a sample of women and men. And this is how many people were that different height. So a couple things that you can see from this, the women's distribution, so the distribution of the heights is taller and skinnier, right? So they have a lot more people right here in the middle, and it doesn't spread as far out. So it doesn't have as big of a range as the distribution of men's heights. So there are some men that were as short as some of the shortest women in the study, and some of the tallest men were taller than the tallest women in the study. So, and the average here for the women was about 66 inches. The average for men was about it looks like 71 inches. And so that are the averages, and you can see women are closer in heights to one another from this sample. And the men there's more variety of heights in the men's sample. So that can tell you something. If this is a big enough sample, you might be able to say, well, that is, because I forget where this data came from. This might actually be national average data from the US, if I remember right. So you can probably say, okay, if we take any person in the US, they probably fall somewhere under this distribution and make assumptions about that or inferences about that. Distributions can look different than that kind of distribution. So here we've got kind of normal distribution with average in the middle being where most people are, and it might be skinnier or spread out more. We could have a distribution like this. This is a distribution of household income in 2014. So while the average is over here, uh, actually the really high numbers pull the average over. So we've got a big bulge over here that is closer to 30,000, where most people are making in 2014 as household income. And there's very few people that are way over here making millions and millions of dollars, but those are such dramatically bigger numbers that it pulls your average over. So that's why people will often not use the average income in the US. They will use the median income, the middle number that they find. And it's still usually higher than this bulge. I think recently I've been hearing like 60 or 70,000. But you can see here in 2014, and wages haven't raised much since then, the bulge was down here at like 30,000. So using this kind of distribution can give you ideas about a better understanding of it. So this was the US Census Bureau data, so it was pretty close, as close as you can get to whole population. So they're trying to get the whole population in the census. Obviously, they're always going to miss some people. Here is one of my studies, some data from a study of heroism, looking at who would claim that they would take heroic action or not. And so this is the age distribution of my study. So we had about, it looks like 64 people who were like 38 in my study. And we had, it looks like 2 people who were like 78 in my study. So if you look at this distribution, you might be able to make some inferences. From this study, I know a lot about people, about their heroism or intended heroism, when the person is like 35 to 50. I know a lot about that group. I don't know very much about people who are from 60 to 80. There were a few in there, so I have some ideas, but not enough data, not as much as this. Right, so that is another thing about the distribution. Lets you know who can you generalize to. I can probably generalize these findings because I did have pretty big samples. I think this study had 600 participants, so that's a pretty big sample from all across the US, a wide variety of ethnicities and genders. So I can probably generalize to a lot of people who are in between about 30 and 50. But beyond that, not sure. Here's another piece from that study. This was how many people said that they would do something pro-social, who would act pro-socially. So higher scores mean, yes, I will definitely act pro-socially. Low scores mean, no, I definitely will not. As we can see, almost everybody in the sample had the 2 highest scores, 6 to 7, as an average. So 7 was the highest score. So this shows me that almost everybody in the sample says that they would act pro-socially, which is nice that they said that they would act that way. But compare this distribution, what that tells you about people, to this distribution. This was the same study, people saying that they would take heroic action. Again, over here is yes, I definitely will. Here is no, I definitely will not. And here we have a lot more people in the middle, which is better if you're wanting to see change over time. So, which is one of the main focuses I wanted for this tool, was be able to measure change over time. So a lot of people are like, well, maybe, yeah, sometimes. And some people are like, definitely not. Some people are like, definitely will. That's what I wanted to see, though, is that a lot of people were like, maybe sometimes. So inferential statistics let us take this data and I could say, all right, I could guess, I could infer that if I had someone who was 44, I would suspect that they would have somewhere close to the average in it, which I think the average in this study was like 4.4 or 4.5. They would get somewhere close to that score on this scale of heroism out of 7. So with that, that's inferential statistics. You take the data from your sample, you make generalizations about the population. So if you have 500 people from across the US, you might be able to make inferences about the people in the US. So if you found a correlation between both well-being and education level, so people who have more education have higher well-being, or people who have higher education have lower well-being, you might be able to infer that about the population. As long as your sample is good, as long as your sample is big enough and varied enough with enough people in it to make inferences about the population. So another big point in the chapter is to conduct ethical research. So there are a lot of examples in this YouTube video of unethical research. I definitely recommend if you want some more examples, you can read that, but the book has some pretty good ones. So there are things like the Milgram experiment, the Stanford prison study, where we really treated participants really poorly. Medicine did this too, treating participants very poorly. So because of that, a thing called the Belmont Report was created. And based on that, the APA, the American Psychology Association, put ethical guidelines out that researchers should follow. So now we have the IRB, the Institutional Review Board. Basically, it's a board of people that if I want to do a study, before I ever collect data or take any steps in contacting participants, I tell the IRB, hey, this is my plan. This is what I plan to do with people. This is how I'm going to keep their data safe. This is how I'm going to keep the people safe. This is all the instructions I'm going to give to them. Basically, you have to give them everything you're ever going to do with these people up front, and then they review it and they say, okay, it looks like you're keeping these people safe. Go ahead and do your study. Or, hey, it looks like you should make some revisions to take better care of people. And that's usually what happens is you might get a couple revisions. So one revision that I've gotten, for example, is make sure the data is stored on an encrypted password protected computer. So that's an example of one thing that I had to revise to make sure the data stayed confidential and nobody could just like grab my flash drive with people's personal data on it. So there are other organizations like the IRB in other countries. So you can look at this link here to find some examples of those. Some of the main things we want for participants, we want them to be informed. We want to give them informed consent. Informed consent is like a step above consent. Consent is, yep, I'll be in your study. I will do this study. Informed consent is, hey, these are the things that are going to happen to you in the study. These are the potential risks that are in the study. These are the kinds of things you might experience in the study. Do you still want to participate? That's informed consent. So it's a little bit different. And we want people to have informed consent. We want them to have all the knowledge that they could possibly need to say yes or no, I do want to and consent to being in your study. So that is one thing that we need to do now. Usually we have like a form that describes what's going to happen in the research. And with that, I'm going to actually jump all the way to deception. You really want to use deception almost never. So there, in the past, and especially in a lot of social psych experiments, there was a lot of deception used to try and trick people in really creative ways to make them do things that were astonishing and surprising. But really, you can learn a lot of those same things without lying to people. It might take some more care and creativity and concern and work at it, but you can definitely learn the same or nearly the same things with telling people honestly what's going on. So as an example, in an experiment I ran, I was testing if a short mindfulness video that helped people do a guided meditation, they either got that as the treatment condition or the control condition of they did a brewery tour. They watched a video of a brewery tour. So they were about the same length. The person guiding the video sounded very similar in both of them. And so that's why we use that as the control condition or comparison condition. So what we told participants up front, like we're going to ask you questions about your mood, like about anxiety and stress. We'll ask about happiness. We'll also ask you to watch a video and follow along with the video. You really shouldn't have any risks other like more than you would get in day-to-day life, just interacting with people. Do you agree to do this study? Like there's obviously more to it, but we told them basically what they were doing. The only thing we didn't tell them was you are going in the treatment group, you are going in the control group. So after they did the videos, after they did the surveys, we said, hey, you were actually part of the control group. You were actually part of the treatment group. We debriefed them about the deception. So that was like the little bit of deception, just not telling you which group you're in. You don't have to completely trick them and make them think something very dramatically different. So use as little deception as possible, and that goes to debriefing as well. Tell participants afterwards exactly what was really going on in the study, especially if you used any kind of deception, and also make sure they leave with no bad feelings towards psychology or the field at large, to you as a researcher. It's also really great if you can give them some skills. So some of the things in my studies, especially when I'm trying to do an intervention, whether it's to make people more pro-social or build purpose in life, the comparison condition is oftentimes to learn some memory skills and memory tricks. Like that's a good thing. You're in the control group, but you're learning something useful for you. So that's also a good thing to do. And the last one here for ethical research is making sure data is confidential. So anybody who reads my research report should not be able to say, oh, this was this kid at this school that got this really low grade on pro-social or this really low score on pro-social behavior. That person's a jerk or something like that, right? You should not be able to be identifying the participants without their consent. You might have a study where you explicitly ask people for their consent to publish their data identifiably, but usually all the data is going to be confidential forever. All right, and so those are the steps that we take now to help people be safe from our studies. And that is the end of the chapter on research. There is a little section on how to review a research article. The main points are abstract, introduction, methods, results, and discussion. So the abstract is a summary of the paper. Here's an example of that. That's a summary of the entire paper that the researchers write. The introduction is kind of the beginning part of the paper right after the abstract. It talks about what inspired this research, what research has come before it, what theory suggests might happen. So this is actually a really great section for you to read if you're writing a research paper. Methods in a 100 level class, you can probably skip the methods and you could probably skip the results. The methods is where the scientists say, these are the scientific methods we used in this study. Results is, here are the actual statistical tests, the statistical results that we found in this study. So again, methods and results at a 100 level class, you can just skip those. Skip all the way to the discussion. Sometimes it'll be labeled conclusion. So that is another place. Now that they have the number results, they will describe it in the discussion and conclusion in kind of more normal language. So what does this mean? Based on previous theory, what should you take away from this paper? That is what the discussion is. So this is also a really great place to look for information when you are writing research papers. So hopefully with this discussion of psychology, getting some of the basics in what psychology is, how science is done, before we jump into some topics around psychology more specifically in the following chapters, hopefully you see how relevant it is for you. Psychology is really learning about you. With this, hopefully you'll find things that are useful in your life, with your family, with working with people, and it will also help you know how to be a better consumer of science. Hopefully you will see errors when media talks about studies. Oftentimes they call any study an experiment, but as a reminder, we've got to have a couple key things for an experiment. It's got to be at least two variables. You got to manipulate at least one of those variables and then measure the other one. So that is a true experiment. If it's just a survey with no manipulation, well, that's probably more of a correlational study, not an actual experiment. So you'll get better at understanding that and understanding the things that you read in your research paper. So thanks for being here, and we'll dive into more depth on some more specific psych topics.